In this Pencast, I am going to calculate delta G, the free energy change of this reaction, three ways. First, I'm going to use standard enthalpies of formation and standard molar entropies to calculate delta G. Then I'm going to use standard free energy changes for all of these substances to calculate delta G. And then we're going to look at how to calculate delta G at a different temperature other than 25 degrees Celsius, which is standard conditions for thermodynamics. So let's get started with the first one, which is using delta H's of formation and standard molar entropies. So I have information in front of me right now. You would have to look this up in an appendix or somewhere for the delta H's of formation. And so we're going to use Huss's law, and we're going to calculate the delta H for this reaction under standard conditions. And the delta H of formation, remember when we do this, we're summing the products times their coefficients, and then the reactants where we change the signs of the reactants. Because remember, reactants are being broken down, they're not formed. So we're using the opposite of the delta H of formation for the reactants. So the delta H for calcium oxide solid is negative, so we have 1 mole of it, because all of these coefficients are 1. So I'm going to be explicit about that, because if you have a coefficient other than 1, you need to multiply it by that coefficient. Okay, so for calcium oxide, and again, you can look these up, solid, we have a delta H of formation of negative 634.9 kilojoules per mole. Okay, and we're going to add that to the delta H of formation of carbon dioxide gas, which is negative 393.5 kilojoules per mole. And by each of these ones I can write moles, and you can see that the moles cancel out, and you'll just get a kilojoules for the reaction as written. And then we're going to add that to the negative of the delta H of formation for calcium carbonate, which is negative 1206.9 kilojoules per mole. Okay, if I do that, if I add all of that together, I will get a delta H of 178.5 kilojoules. Okay, so that's the delta H. And remember that our goal is to calculate delta G eventually, but you need, in this method, you need delta H and delta S to do that, because you have an equation that relates delta G to delta H and delta S, which we will see in a moment. So for delta S, we are going to use the standard molar entropies. Again, you would have to look these up. I have them in front of me. Again, we have 1 mole of the calcium oxide, which is 38.1 joules per mole Kelvin. And we're going to add that to 1 mole for the carbon dioxide, which is 213.8 joules per mole Kelvin. And we're going to add that to the negative of the reactant, which is calcium carbonate. I wasn't explicit, but I was multiplying that by 1 mole up there. I'm going to multiply this by 1 mole times the negative of 92.9 joules per mole Kelvin. Okay, if I do that, I will get, for my value of delta S, 159.0 joules per Kelvin. Okay, now what do I do with this information? My goal is to calculate delta G under standard conditions, and we know that delta G equals delta H minus T delta S. So we've calculated our delta H's using enthalpies of formation, our delta H using enthalpies of formation, and we've calculated our delta S using molar entropies, and we know the temperature because we're told to calculate this under standard conditions, which is 25 degrees Celsius. So we should be able to use this equation to derive delta G. There's one hitch, and you have to really pay attention to your units here. This is the enthalpy is reported in kilojoules, and the entropy is reported in joules. This is a problem that you're going to run into every time you use these standard values, just because of how they're reported normally in these appendices. So you have to convert either enthalpy to joules or entropy to kilojoules. I'm going to convert entropy to kilojoules, just because to me it makes the calculation a little easier. And so I'm going to divide by 1,000, and I'm going to put my decimal point 3 back to show that I'm dividing by 1,000. 0.1590, so this is equal to 0.1590 kilojoules per Kelvin. Okay, bigger unit, so smaller value. Okay, now I can do this. So delta G equals 178.5 kilojoules, that's my delta H, minus, now for temperature I have to report temperature in Kelvin. I always have to use Kelvin units in these calculations, these thermodynamic calculations. And so 25 degrees Celsius is, you just add that to 273.15 because that's our 0 Kelvin value, plus 25, or that's our 0 degrees Celsius value, I should say. 273.15 equals 0 degrees Celsius, but we have 25 degrees Celsius, and so that comes out to be 298.15 Kelvin. So we multiply that times our delta S, which is 0.1590 kilojoules per Kelvin. Notice that this is 298 Kelvin. This is going to, well, 0.15. This is going to cancel out with the Kelvin units in entropy, and we're going to come out with a kilojoules unit for our answer for delta G. And that turns out to be 131.1 kilojoules. So that's how to use this equation along with delta H's of formation and standard molar entropies to calculate delta G. But you'll also notice, if you look at most thermodynamic tables, data tables, you'll also notice that for most substances, there are standard free energies of formation of these compounds that are listed. So these look like that, okay? And they're listed alongside other data, the delta H's and the S's in thermodynamic tables. And this is the free energy associated with formation from standard state elements. Okay, so that's just like the delta H's of formation, only we're reporting the delta G's of formation instead, and just like delta H's, standard state elements have a free energy of, a change of free energy of 0 associated with them. So we just look these up and we use Hess's law because delta G is a state function just like delta H and delta S are. And so we are going to use our Hess's law where we'll say delta G, and we're going to look these values up on data tables. If I look up, and I'm forming the reactants, so I don't change the signs. but I'm breaking down, sorry, I'm forming the products, so I don't change the sign, but I'm breaking down the reactants, so I do change the sign for the reactants. So what that means is I'm going to take the delta G value for calcium oxide, which is, and I'm going to multiply it by 1 mole because that's how much I have, which is negative 603.3. These are reported in kilojoules per mole. Okay, I'm going to add that to 1 mole times the delta G of formation of carbon dioxide, which is negative 394.4 kilojoules per mole. And I'm going to add that to 1 mole times the negative of the reactant, which is calcium carbonate, which is negative 1128.8 kilojoules per mole. Sorry if you can't see that, that's kilojoules per mole. And if I do this, I will get 130.4 kilojoules. So it's a little easier way to do it. You'll see that it's, you know, slightly different from the value above it. And that's because these are all theoretical values that are based on measurements, and they can be slightly off from each other, but that's pretty close. So the third thing that I want to do is I want to calculate delta G at a different temperature than 25 degrees Celsius. So I'm going to say delta G at, what if it's 0 degrees Celsius instead of 25 degrees Celsius? We are going to assume that the delta H's and the delta S's don't deviate very much with different that the delta H at least doesn't deviate very much with different temperatures, and we have a temperature term in our equation to modify the delta S. So again, we're going to use our delta G equals delta H minus T delta S, and this time, so we are going to use our same values for delta H and delta S that we calculated using the enthalpies of formation and the standard molar entropies, but we're going to multiply it by a different temperature. So 178.5, so this is 1 mole again, times 178.5. Well, actually, no, this is just for the reaction. So we've already crossed out the 1 moles, and we're saying that this delta H value here is the delta H value for this reaction as written, where 1 mole of calcium carbonate reacts and forms 1 mole of calcium oxide and 1 mole of carbon dioxide. So this is just a straight kilojoules value. So this equals 178.5 kilojoules minus T. So this time temperature is not 298, it's 273.15 Kelvin, and then times our delta S value here, which is 159, oops, I almost fell into the trap of not converting my units, 0.1590 kilojoules per Kelvin. Remember, I have to keep them all in either kilojoules or joules. Our kelvins cancel out, and what we get here is 135.1 kilojoules. So practice doing this yourself using the thermodynamic data that you have in your textbook appendix, or just looking it up online. Give yourself some reactions that actually have some different coefficients here than 1. This is kind of a simple example, but what if you had a 2 or a 3 in front of that? Well, that means that you would just multiply it by that coefficient in all of these calculations here, because the delta H's, the delta S's, and the delta G's that we're calculating are for the reaction as written when we're interpreting the coefficients as the number of moles reacting and forming. So try these, practice a whole bunch of them, get fluent with them, and doing the number 1 and the number 2 procedures can help you check yourself to see if your calculations are right, because they should come fairly close to each other.